carrying on looking at this idea of trig substitutions, but just going to look at a couple of specifics here. Situations like this, where you see the square root of something, and there's two terms in there, and they're two squares. This lends itself to trig identities, because it will allow us to get two terms, pull it into one. So if I've got a squared plus x squared, then I'll use the substitution a tan theta, because I know tan squared plus 1 is sec squared. I can bring it back into one trig term. If I see a squared minus x squared, then I'll use either sine theta or cos theta. It doesn't really matter. Let's say it was sine theta, because 1 minus sine squared is cos squared. Again, I can pull it into one function. And if it's the other way around, and I have x squared minus a squared, then I'll use the substitution sec theta, because sec squared minus 1 is tan squared. When you rearrange our 1 plus tan squared is sec squared. This is one of those non-standard rules where I've said, oh, it's easier just to remember the answer. But this is where it comes from. You have 1 on the square root of a squared plus x squared. So I will use a tan theta. The derivative then becomes a sec squared theta. So substituting back in, dx is a sec squared theta. The bottom of the fraction, a squared plus a squared tan squared, but as I say, we can pull that together now and say that's a squared sec squared, and the square root of a squared sec squared is a sec, but a sec will cancel into the a sec squared, leaving us with just sec theta. And the integral of sec is the log of sec plus tan. Now I just have to try and get the x back in here. Well, how do I do it? That's when I just draw myself a triangle. We said x was a tan theta. In other words, the tan ratio is x on a. That's how I label my triangle. The hypotenuse, not a coincidence, it turns out to be our square root. Let's now sub in. Sec theta, well, sec's the reciprocal of cos. So it's hypotenuse over adjacent. Tan is opposite over adjacent. There's our answer, but that's not how we generally remember this integral. And here's why. Notice they're both over a. I could use my log law and say, well, that's minus the log of a. But the log of a is a constant number. So I can absorb it with the other constant and just say, well, look, it's this plus some constant. And that's generally how we remember the integral, without the on a part. But that's where it comes from, should they ask us to actually go and work that one out. Now, this one, I would hope you would look at it and see, oh, hang on, we've got derivative on function situation here. That would, in my opinion, be the quickest way of doing it. But if you did look at it and say, hey, I've got this square root sign, it's 1 minus x squared, so why don't I do a substitution, x equals sine theta, dx becomes cos theta to theta. So my integral now becomes x, sine theta, dx, cos theta to theta, over the square root of 1 minus x squared, 1 minus sine squared. 1 minus sine squared is, of course, cos squared. Square root of cos squared is cos, which will cancel with the cos in the top of the fraction, and I just have the integral of sine. Integrate sine, that's minus cos. Again, let's draw a triangle up. We said x was sine theta. So opposite over hypotenuse is x over 1. The third side, again, not a coincidence, is our square root. We want cosine, which is adjacent over hypotenuse, and there's our answer. I still think just seeing derivative on functions is probably quicker. But anyway, it's your choice, of course, how you want to integrate something like that. Square root of x squared plus 3. So this one I'll do root 3 tan theta. So the derivative becomes root 3 sec squared theta. What do I get? Well, dx, there's the root 3 sec squared theta to theta. The root x squared plus 3, I've done it all in one hit this time, but that would have been 3 tan squared plus 3. 3 tan squared plus 3 is 3 sec squared. The square root of 3 sec squared is root 3 sec. That's where I've got that number from. Multiplying out, we get 3 times the integral of sec cubed, and that's when we now start crying, because as we saw yesterday, if it's sec to an odd power, oh, I've got to use parts to do this. Okay, sec cubed, let's split it up into the 2 parts I'm going to work with. One's sec, one's sec squared. I guess, obviously, if I'm going to split it up, because how else could I do it? the only combination of 3 when I add two numbers together is going to be 1 and 2, or 3 and 0, so it's got to be 1 and 2. We'll let u equal sec theta, du is sec theta tan theta, then dv becomes sec squared. Integrate sec squared, we get tan. So I have 3 lots of uv, sec theta tan theta, minus 3 lots of v du, which becomes sec theta tan squared. Okay, but now the tan squared I can change to sec squared minus 1, multiplying by the negative 3, we now have 2 integrals, minus 3, the integral of sec cubed, plus 3 times the integral of sec theta. Well, I can work out the integral of sec theta, we know that, it's the log of sec plus tan. Minus 3 times the integral of sec cubed theta to theta. If you have a look at my third line, we're saying, hang on, this equals 3 times the integral of sec cubed theta to theta. So to make it a little bit easier for myself, I'll substitute in now. But here's my substitution. Yeah, I've got to work out the sec theta and the tan theta, so I draw my triangle. Tan is x on root 3, so the hypotenuse, again, not a coincidence. There it is, the square root of x squared plus 3. And look at my substitution. I've substituted in for sec theta, square root x squared plus 3 on root 3. I've substituted in for tan theta, x on root 3. I've substituted in for 3 times the integral of sec cubed theta. Now I haven't bothered to go to the lengths of this one. I've just said, hang on, I know, because look at my third line, that 3 times the sec cubed of theta is the integral of the square root of x squared plus 3. So that is what I'm going to substitute in for 3 times the integral of sec cubed theta. And then plus the log, again, substitute in for the sec theta and the tan theta. But now I can move that integral of the square root of x squared plus 3 to the left-hand side of the first line, and I end up with this. 2 times the integral of the square root of x squared plus 3 is x squared plus 3 log. There is an answer, and I guess it's fine, but yeah, I'm going to get rid of that log root 3 and absorb it in the constant. Do you need to? I guess not. I mean, the second last line is an answer. It's certainly correct. I guess there's no reason why you couldn't leave it like that. But I tend to do it that way. Our textbook doesn't really have an exercise specifically on this, so I've grabbed an old exercise from the very old Patel textbook now. Wow, yeah, it is old, but it is in the handout. It's photocopied, it's in there for you. So exercise 2E, looking at these sort of integrals.